A very warm wishes to you all. I am Dr. Onika Parmar and today we are going to discuss about metal semiconductor junctions and heterojunction. We will be exploring this exciting area of electronics at an atomic scale. So, these are the outlines of today's class. We will discuss about metal semiconductor junctions, in which we will discuss about ohmic contacts, n-type semiconductors whose work function of metal is smaller than work function of semiconductor, ohmic contact for p-type semiconductors where work function of metal will be greater than the work function of semiconductor. We will discuss about metal semiconductor junctions for rectifying contacts for the n-type semiconductor and p-type semiconductor. For the n-type semiconductor, work function of the metal will be greater than work function of silicon, and for p-type semiconductor, work function of metal will be less than work function of silicon. We will also discuss about heterojunctions, electron affinity rules and band alignment, type of heterojunctions, p-n heterojunctions diode in equilibrium condition. So, let's start with metal semiconductor junctions. Many of the useful properties of a p-n junction can be achieved simply by forming an appropriate metal semiconductor contact. This approach is obviously attractive because its simplicity of fabrication, and also, as we shall see in this section, metal semiconductor junctions are particularly useful when high speed rectifications are required. The high speed rectification are the major application where we use metal semiconductor junctions. In many cases, we wish to have an ohmic metal contact with semiconductor contact having a linear IV characteristics. IV is current voltage characteristics. So, in both biasing directions. For example, the surface of a typical integrated circuit is a mesh of p-n region which may be contacted and interconnected. It is important that such contact be ohmic with minimal resistance and no tendency to rectify signals. If we see an integrated circuit, we will find there will be a layer of p and n regions, and these all regions has to connected, and we use metals for the interconnects. So, when a metal is connected with the semiconductor, we want that contact to be ohmic. If that contact is ohmic, it will not rectify any signal, it will not omit any signal, and we will have a linear VI characteristics for it. Hence, we require the contact with minimal resistance and no tendency to rectify any signals. So, ideal metal semiconductor contacts are ohmic when the charge induced in the semiconductor is aligned with the Fermi level provided by the majority carriers as shown in figure 1. Here we can see there is a metal and there is a semiconductor. Let's suppose the example of a n-type semiconductor. Here we can see in the figure when a metal is brought in contact with an n-type semiconductor. So, the electrons from the n-type semiconductors come to align the Fermi energy level. Here we can see in a n-type material the negative charges come. Hence, we can say, so ideal metal semiconductor contacts are ohmic when the charge induced in the semiconductor is aligned with the Fermi level provided by the majority carriers. Here we see that the charge provided are because of the majority carrier of the n-type material. In the n-type material, the majority carriers are electrons. So, electron came to align the Fermi energy level. So, such type of contacts are ohmic contacts. So let's take another example. For example, if we bring a metal with work function phi m in contact with the semiconductor, let's suppose the semiconductor is a n-type semiconductor and phi s symbolizes the work function of the semiconductor. So let's discuss about the n-type semiconductor. As we can see for the case 1 of figure 1a. The Fermi levels are aligned at equilibrium by transferring electrons from the metal to the semiconductor. This raises the semiconductor electron energies, lowers the electrostatic potential relative to the metal at equilibrium in figure 1b. In this case, the barrier to the electron flow between the metal and the semiconductor is so small and easily overcome by a small voltage. So, in the ohmic contact, continuous flow of charges occur in the n-type semiconductor. For forming an ohmic contact, the work function of the metal, which is represented as phi m, should be less than the work function of the semiconductor, which is represented as phi s. Here we can see there are two figures, figure A and figure B. Here we can see the work function of the metal is smaller than the work function of the semiconductor when they both are brought in contact. The electron from the semiconductor, n-type semiconductor, where the electrons are the majority carrier, they come at the metal semiconductor junctions and hence the Fermi energy level is aligned for the metal and the semiconductor, forming an ohmic contact. So hence for an n-type semiconductor to have a ohmic contact, phi m must be less than phi s. Work function of the metal should be less than the work function of silicon. Let's take the case for a p-type semiconductor. That is, we want to make a ohmic contact for a p-type semiconductor. So, in the case of a p-type semiconductor, the work function of the metal, which is represented as phi m, should be greater than the work function of the semiconductor, which is represented as phi s. Similarly, as we have discussed, the case for phi m greater than phi s for a p-type semiconductor results in easy hole flow across the junction in figure 2a. Unlike the rectifying contacts, no depletion region occur in the semiconductor in these cases, since the electrostatic potential difference required to align the Fermi energy level at equilibrium calls for accumulation of majority carriers in the semiconductor. So, here we are making a metal semiconductor contact for a p-type semiconductor material. So, in case of a ohmic contact, as I have told you earlier also, there is a continuous flow of carriers in the p-type semiconductor when the work function of metal is greater than the work function of semiconductor. Here we can see two figures. This shows the energy band diagram, and the first one, figure A, is for before any contact and the second one is after the contact. Here we can see that in the figure A, there is the energy band diagram for the metal and the semiconductor when they are not connected to each other. Here we can see that the work function of metal is greater than the work function of semiconductor, and when they are both joined together, the holes from the p-type material comes at the contact of metal and semiconductor junction, and the Fermi level aligns because of this accumulation. Hence, the contact is formed, and such type of contact is an ohmic contact. Thus, to form an ohmic contact, the semiconductor which is connected with the metal, the majority carrier of the semiconductor must align at the metal semiconductor junction. When the majority carriers align with the metal semiconductor junctions, ohmic contact is formed and the characteristics are almost linear. So, in the case of a ohmic contact, there is a continuous flow of charges. Metal in contact with the semiconductor, charge transfer causes alignment of Fermi energy level. Hence, we can define work function as the energy required to remove an electron from Fermi energy level to vacuum. A practical method for forming ohmic contact is by doping the semiconductor heavily in the contact region. Thus, if a barrier exists at the interface, the depletion region width is small enough to allow the carriers to tunnel through the barrier. Now comes rectifying contacts. So, first we will discuss about the N-type semiconductor. To form a rectifying contact, the work function of the metal should be greater than the work function of the semiconductor. When a metal with work function phi m is brought in contact with a semiconductor having a work function phi s, the charge transfer occurs until the Fermi energy levels are aligned to each other, as we can see in figure 3. So, here there are two figures. First one is the discrete case when a metal is not in contact with the semiconductor, and second is when the metal is brought in contact with the semiconductor. So, here we can see that the work function of the metal is much greater than the work function of the semiconductor, and here we are using N-type semiconductor. Now, we want for the alignment of the Fermi energy level, we want that the Fermi energy level should be shifted downwards, or in the case of the metal, it should be moved upwards. So, to have such actions, there should be some positive charges at the N-type of the semiconductor. Now, the positive charges will come at the metal semiconductor interface and the Fermi energy level will shift downwards, and there will be a positive depletion region formed, and thus there will be a alignment in the Fermi energy level. Now, we can see that in the figure there is metal, then there are positive charges, then a semiconductor. Actually, those positive charges are the part of this semiconductor itself. So, there is a depletion region which is being formed in the figure. So, let us go through this example once again. When metal with work function phi m is brought in contact with the semiconductor with work function phi s, and the work function of the metal is greater than the work function of the semiconductor Fermi energy level is initially higher than the metal before the contact is made. To align the two Fermi energy level, the electrostatic potential of the semiconductor must raise, that is, the electron energies must be lowered relatively to that of the metal. In the N-type semiconductor of figure 3, a depletion with W is formed near the junction. The positive charge due to the uncompensated donor ion within W matches the negative charge on the metal. The electronic field and the bending of the bands within W are similar to effect the already discussed of p-n junction. So, for rectifying contact of a N-type semiconductor, work function of the metal should be greater than the work function of the semiconductor. The equilibrium contact potential is represented as V0. It is equal to phi of m minus phi of s, that is the difference between the work function of the metal and semiconductor. Depletion region width W, like in a p plus plus n junction, the potential barrier height phi b is equals to phi m minus the electron affinity, blocks the electron injection from metal to the semiconductor. The junction capacitance is represented as epsilon A by W. the metal in contact with the semiconductor, the charge transfer causes alignment in the Fermi energy level. So, in the cases when we have a rectifying contact, we can see from the figure there is a metal and there is a n-type semiconductor, and to align the Fermi energy level, in this case there has to be a induction of positive charges and a depletion region width W is generated between the metal and the semiconductor, and here a rectifying contact is formed. So, for the condition to form a rectifying contact with a n-type semiconductor, in these cases the work function of the metal should be greater than the work function of the semiconductor, and the equilibrium contact potential is the difference between the work function of the metal and the work function of the semiconductor. In the cases, the junction capacitance is given as epsilon A by W. This is also represented as CSB. For figure 4, the illustration of a Schottky barrier on a p-type semiconductor with work function of the metal less than the work function of the semiconductor. This is the case for a p-type semiconductor. To have a rectifying contact with a p-type semiconductor, the work function of the metal should be less than the work function of the semiconductor. In this case, aligning the Fermi levels at equilibrium requires a positive charge on the metal side and a negative charge on the semiconductor side of the junction. The negative charges is associated by depletion region W, which ionized acceptor Na, the ionized acceptor are represented as Na, are left uncompensated by holes. The potential barrier V0 regarding the hole diffusion from the semiconductor to the metal is phi s minus phi m, that is the difference in the work function of the semiconductor minus the work function of the metal, and as before, this barrier can be raised or lowered by the application of voltage across the junction. Hence, to form a rectifying contact with a p-type semiconductor, the work function of the metal should be less than the work function of the semiconductor. So, there are few equations which we should remember, and a few of them are shown here. Here there is a p-type semiconductor. As we can see in the figure, it is brought in contact with the metal, and the work function of the metal here is less than the work function of the semiconductor. So, here we can see that there is a p-type semiconductor and a metal with work function less than the work function of the semiconductor is brought in contact. Now, what happens here? The minority carriers of the semiconductor aligns at the metal semiconductor contact, and a depletion region width is formed, and this depletion region width in maximum cases is represented as W. So, there is a region of metal and then the minority carriers and then the majority carriers of the semiconductor. So, a rectifying contact is formed here as shown in the figure. The bend bending diagram is represented in figure B as the metal is brought in contact with the semiconductor. For the equilibrium condition, the contact potential V0 is given as the difference between the work function of the semiconductor and the metal. So, phi of S minus phi of M. This blocks the whole diffusion from the semiconductor to metal. Depletion region width W like in a N++ P junction. So, the depletion region will look like the junction contact where we have a heavily doped N-type material and a P-type junction. The potential barrier height is given as phi b, and the equation here is given as energy gap by Q plus electron affinity minus phi of m. Phi of m is the work function of the metal. This blocks the whole injection from the metal to the semiconductor. So, rectifying contact to form a Schottky barrier diode. So, these are the applications of a rectifying contact. With the help of a rectifying contact, we can make a Schottky barriers. These have various applications in the form of diode. So, we are here discussing about the Schottky barrier diode. So, for an n-type semiconductor, phi of m must be greater than the phi of s. Here phi of m is the work function of the metal and phi of s is the work function of the semiconductor. And in this case, we can see the current voltage characteristics in the figure, and we can see that the y-axis has the current value and the x-axis has the voltage value, and we can see there is a change in the current in an exponential manner, which is given by the equation I is equals to I naught in bracket e to the power of qv by kt minus 1. This is the current equation for the Vi characteristics of the diode, and the I naught is given by the equation as shown in the screen, and the work function here is 0.7 to 0.9 in case of the silicon. So, here we can see that the term ITH is an important term. It is thermonic emission electron flux from metal to the n-type semiconductor, current from the n-type semiconductor to the metal across the barrier phi b. So, let us discuss about it forward bias condition. So, when a forward bias voltage V is applied to the Schottky barrier, the contact potential is reduced from V0 to V0 minus V, as we can see from figure 7a. As a result, electron in the semiconductor conduction band can diffuse across the depletion region to the metal. This gives rise to a forward current from the metal to the semiconductor through the junction. Consequently, a reverse bias increases the barrier to V0 plus Vp, and the electron flow from the semiconductor to the metal becomes negligible. In either cases, the flow of the electron from the metal to the semiconductor is retarded by the barrier phi f m minus electron affinity. Electron affinity is represented as psi. So, at equilibrium condition, IDIF is equals to ITH and the net current here is 0. In forward bias condition, diffusion electron increases from n-type semiconductor to metal due to the lowering of V0 by V. The thermonic emission electron from n-type semiconductor across the barrier phi b remains unchanged, and the diffusion current is greater than the ITH. The net current from the metal to the semiconductor is greater. The net current flows from the n-type semiconductor to the metal, and the equation is shown here. Here is the figure for the forward bias condition. Here we can see the metal is brought in contact with the semiconductor. Now, let us discuss about the reverse bias condition. For the reverse bias condition, the diffusion electron flow from n-type semiconductor to metal is reduced due to increased V0 by Vt. The thermonic emission electron from metal to n-type semiconductor across the barrier phi b remains unchanged, but a small current flow from n-type semiconductor. Here also the flow of electron flows from the metal to n-type semiconductor, and the equation of the current is given as shown in the figure. Here I is equivalent to the negative of I naught. In both these cases, the Schottky barrier diode is rectifying with easy current flow in the forward direction and a little current in the reverse direction. We also note that The forward current in each case is due to the injection of the majority carriers from the semiconductor into the metal. The absence of minority carriers injection and the associated storage delay time is an important feature in Schottky barrier diodes. Although some minority carrier injection occur at high current levels, these are essentially majority carrier devices. Their high frequency properties and switching speeds are therefore generally better than a typical PN junctions. Now let's discuss about heterojunctions. Heterojunction is an important class of junction consists of those between the two lattice mismatched semiconductors with different band gaps. So let's consider there are 4 different kinds of commonly encountered heterojunctions. So there is a PN heterojunction diode, NN heterojunction diode, PP heterojunction diodes and quantum wells. We also call it as quantum wires or quantum dots. So consider a junction of a p-doped semiconductor, that is semiconductor 1, with a n-doped semiconductor, that is semiconductor 2. The two semiconductors are not necessarily of same, it can be any one. There can be two types of semiconductor, like one can be gallium and second can be arsenide, or one can be aluminium gallium arsenide and the second could be gallium arsenide. So it's not necessary that both the semiconductors should be the same. It's not necessary that one should be silicon and second should also be silicon. So one can be of, let's say an example of aluminium gallium arsenide and second of gallium arsenide. When they both are brought in contact, so we are discussing how these two can be brought in contact. So we assume that one has a wide band gap than the second one, and the band gap of the 1 and 2 by themselves are shown in figure here. Here we can see the energy band diagram for two different type of semiconductor. One has higher energy band gap than the second one. We can see in the second figure the difference between the conduction band and valence band is smaller, while in the first case the difference between the conduction band and the valence band is larger. So we can see the energy gap for both the cases, both the semiconductors are different. Let's take the example for aluminium gallium arsenide and gallium arsenide. The vacuum level is the energy of a free electron or electron outside from the semiconductor which is at rest with respect to the semiconductor, and the electron affinity is denoted by Xi. For a semiconductor is the energy required to move an electron from the conduction band bottom to the vacuum level is a material constant. The electron affinity is a material constant. It will vary with different material. So here we can see that both the semiconductors are brought in contact to each other. Here we can see the first semiconductor has different energy gap than the second semiconductor. The electron affinity rule for band alignment says that the heterojunction between different semiconductors, the relative alignment of the band is dedicated to their electron affinities. The electron affinity rule implies that the conduction band and offset at heterojunction interface is equal to the difference in the electron affinities between the two semiconductors as shown in figure. According to the electron affinity rule, the conduction band offset is referred as delta EC, is given as this equation as shown in the slide. Delta EC is equals to Q in bracket electron affinity of the second semiconductor minus the electron affinity of the first semiconductor. The valence band offset is given as delta EV. Note that delta EC plus delta EV is equals to delta EG. Depending upon the difference between the electron affinity of the first semiconductor and the second semiconductor, we could have type 1, type 2 or type 3 heterojunctions interface as shown in the figure. These are the various type of the heterojunctions. Type 1 has the example for aluminum gallium arsenide and gallium arsenide. Type 2 are these semiconductors, and type 3 are for broken gap semiconductors. Here we can see the different energy gap alignment for type 1, type 2 and type 3 semiconductors or type 3 heterojunctions. Built-in contact potential is divided between the two semiconductors as required to align the Fermi energy level at equilibrium as shown in the figure. The resulting depletion region on each side of the heterojunctions and the amount of built-in potential on each side making up the contact potential V0 are found by solving the Poisson's equation with the boundary conditions of continuous electric flux density at the junction. The barrier that electrons must overcome in moving from the n side to the p side may be quite different from barriers of hole moving from p to n side. So, this is the figure for band discontinuities and band bending at the equilibrium for p-n heterojunction diode in equilibrium condition. So, thus in this lecture we have discussed about metal semiconductor junctions with ohmic contact and rectifying contact. We have discussed about heterojunction, electron affinity rule and band alignment, types of heterojunction and p-n heterojunction diode in equilibrium condition. So, thank you for attending this lecture. See you in the next lecture.